Alright, AP Chemistry, this is the last part of Chapter 4, and this is balancing redox reactions using the half reaction method. Oxidation reduction reactions, the driving force is a transfer of electrons, which we've discussed before. Again, metathesis, the removal of two ions from solution. Redox, the transfer of electrons. We have a little mnemonic you can use to remember. And the first one is oil. Oxidation is loss of electrons, and when you lose electrons you become more positively charged. Reduction is the gain of electrons. So oil, rig, oxidation is lost, reduction is gain of. Covers the ones we just talked about in the last video. Synthesis, decomposition, the three types of single replacement. Metal replaces another metal, metal and hydrogen, halogen, disproportionation, and combustion. These are all the redox reactions. Alright, balancing redox reactions in acidic solution. First, assign oxidation states to everything in the given reaction. Write out the half reactions. I'm going to tell you right now, I always write out the reduced first. Balance all the elements atomically except oxygen and hydrogen. Leave them for last. Meaning if you have two chlorides here, and then you got to put a 2 in front of this guy. Alright? Don't forget this step. It's going to mess you up if you forget it. Balance the oxygens next by using water. Balance the hydrogens after balancing the oxygens, after balancing it, by using the hydride ion. Use the ion to balance them, not the hydrogen gas or anything like that. Balance the charges by adding electrons. The reduced half reaction will always gain electrons, so put the number of electrons on the left side of the arrow. The oxidized half reaction will always lose electrons, so that goes on the right side, the product side. So here's another little mnemonic. You're reduced. The electrons appear on the reactant side. So there's another little tool to use. Equalize the quantity of electrons in both half reactions. You can't gain 8 electrons if the other substance is only losing 3. So you got to balance the quantity of electrons. Add the half reactions together. Remember, if it's identical on the same side of the arrow, add them up. If it's on opposite sides of the arrow, subtract. Finally, and always check your work, your final product, using the half reaction method of balancing for redox will always be atomically and electrically balanced. So we're going to do examples. Here's example number 1. Potassium dichromate is a bright orange compound because of the dichromate that can be reduced to a blue-violet solution of chromium ions. So bright orange for the dichromate, blue-violet for the chromium ions. Most of your transition metals are very colorful in solution. Under certain conditions, the potassium dichromate reacts with ethyl alcohol as follows. Notice the reaction given is the net ionic equation, and that is usually the reaction you will be given on the AP exam, in the net ionic equation form. We are going to start, and you just follow the rules. And I'm going to drop the states of matter. I'll put them in my finished product. They just kind of get in my way. So here's step number 1. Assign oxidation states. ion, so plus 1. Oxygen is a -2 unless it's a peroxide or attached to fluorine. It is neither, so -2. 7 times 2 is a -14. -14 plus some number multiplied by 2 equaling -2. That number is going to be plus 6. Oxygen's a -2. This is a plus 1. This is a plus 1. This is going to be a -2. This is a plus 3. This is a -2 plus 4. -2 plus 1. So what I want you to establish here, and what I'm going to draw, is the fact that and I go for the reduced half reaction first, this chromium went from a plus 6 to a plus 3. So it's been reduced, therefore it is the oxidizing agent. You're going to have both. Something that's been reduced, something that's been oxidized, an oxidizing agent and a reducing agent. Then the carbon is becoming more positive, so it is being oxidized, and it is the reducing agent. So what I'm going to do is break those down into half reactions. And I'm going to label them. And again, I always go for the reduced first. It's easier for me to spot. So my reduced half reaction, and I'm going to leave myself some room so I can add in, follow the rules. And my oxidized half reaction, alright, so I rewrite the two half reactions, and you will find me always doing the reduced. Okay, step 1, I assigned oxidation states. I figured out what substance was being reduced and what is being oxidized. I always put them in that order. And I rewrote the two half reactions. You will notice I'm only interested in these substances. The chromium ion went from the plus 6 to the plus 3, and the carbon in the ethanol went from a -2 to a plus 4. So that's all I'm interested in. Next step, balance the non-oxygen hydrogens first. I need to put a 2 in front of here, and I need to put a 2 in front of here. That balances my carbons in this one and my chromiums in this one. So they're balanced. Next step, balance the oxygens using water. I have 7 oxygens here. I need 7 oxygens here. I have 1 oxygen here and a total of 4 over here, so I need 3 of them. Now this is really important. You will notice that the waters are on opposite sides of the arrow. They're on the right hand side for the reduced and the left hand side for the oxidized. Will it always be that way? Not necessarily right and left, but they're always opposite too. So if they turned up to be on the left hand side of the reduced, then they'd be on the right hand side of the oxidized. They are usually on opposite sides. Next step, balance the hydrogens. When I added the water, I added hydrogen atoms to the right hand side. So I need to balance that atomically. 14 hydrogen atoms. I have a total of 6 and 6. I have a total of 12 over here on the left of my oxidized. So I need 12. Alright. I am atomically balanced in both my half reactions. What I have to do now is tally up the charges. I have to deal with electrons now, which means charge. The entire side of my reduced, the entire left side of my reduced, positive 14 minus 2, that's a positive 12 charge on the left. 2 times 3, that's a positive 6 on the right. Reduced means a gain of electrons. In order to go from 12 to a positive 6, you need to gain 6 negatively charged electrons, because a positive 12 and a negative 6 will give you positive 6. Now, for the oxidized, oxidized is loss of. The number of electrons will be on the right-hand side, opposite to reduced. Again, there's your opposites. Look at all the opposites. Hydrogen, opposite. Water, opposite. Electrons, opposite. I am going to lose electrons in my oxidized half reaction. I have to figure out how many. Compound neutrally charged, the overall electrical charge of the left side of my oxidized half reaction is a 0. The right side, compound neutrally charged, this is 12 times a plus 1, a total of plus 12 electrical charge. In order for them to be equal, 0 to plus 12, I must lose 12 electrons. Okay, so far so good? Alright, now next step, I must make the number of electrons transferred equal. I cannot lose 12 and have the other guy only take 6. What happens to the other 6? That's like asking the banker to break your $10 bill and they only give you 5 singles. It's wrong. These two numbers, this guy right here and this guy right here, must be equal. So what I'm going to do is multiply this entire half, and only this half, by 2. So what I'm going to do now is I'm going to do the multiplication, I'm going to clean it up, and I'm going to rewrite it. 2 times 14 is 28 hydrogens. 2 dichromates, I never rewrite this. These are balanced, so I don't rewrite them. It's redundant. I did this multiplication in order to make this a 12. Don't rewrite it. 3 waters from my oxidized. My arrow. 4 chromiums. 2 times 7, that's 14 waters. 2 carbon dioxides, and 12 hydrogen ions. Next step, clean it up and insert your states of matter. If it's on opposite sides of the arrow, it's a subtraction. Same side, it's an addition. Notice I have 28 hydrogens here and 12 there. 28 minus 12 is going to be 16 left over on this side. So I have 16 hydrogens. It's an ion, so it's an aqueous. 2 dichromates on the left, none on the right, so it stays as it is. It is an ion, so it is aqueous. I have 3 waters on the left, 14 on the right. 14 minus 3 is 11. Cancels out those guys. Let's see, alcohol is nowhere else, so my alcohol stays put. and it is a liquid based on the previous state of matter from my original problem. I have 4 chromium ions, none on the left, so it stays put. If it's an ion, it's aqueous. I have my 11 waters from when I subtracted the 3 from the left. Water is a liquid. And I have my gaseous carbon dioxide. Alright, so here's my finished product. Now, here's what I want to do. I am going to check it atomically and electrically. 16 hydrogens plus 6 more, that's 22. 11 times 2, 22 hydrogens. Atomically balanced hydrogens, good start. 2 times 2, 4 chromiums, 4 chromiums. 2 times 7 is 14, plus 1 is 15. On the right hand side I got 11 from the water, plus 4, that's 15. So I'm doing good so far. 2 carbons and 2 carbons. I am atomically balanced, so that's a good start. Now electrically, positive 16 minus 4, that's a positive 12, plus 0 stays a positive 12. 4 times 3 is a positive 12. The water is 0, the carbon dioxide is 0. I am electrically balanced. Yeah, done. Awesome.